The overview presentation is by Professor Facchi from University of Bari, and the title of the talk is Control and Dynamical Decoupling.
Thank you, Daniel. Thank you, Dana and Robin for inviting me here. We're happy to be here. It's a very beautiful place, and the conference is very successful so far. And okay, so I was asked to give an introductory talk on quantum control and dynamical decoupling. In fact, I will mainly talk about dynamical decoupling. We'll make some comments, quantum control. And okay, so what is dynamical decoupling? Dynamical decoupling is a powerful strategy in order to suppress the interaction between, for example, the system and the environment. So you want to build up, I don't know, quantum computer, something that works in a coherent way, and you want to suppress all possible sources of decoherence. And essentially, the idea is quite simple. The idea is just to apply a sequence of pulses. You just can think at a sequence of classical fields on the system in such a way that the interaction between the system and the environment averages out. So in this sense, this is an open loop quantum control technique, let's say. But the difference is that you don't know what is the interaction between the environment and the system. So you want to essentially you want to suppress that interaction without having any knowledge about it. This is the first point. The second point, you're allowed to act only. So you don't know the environment, you don't know the interaction. You can only act on the system itself. Okay. And the idea, in fact, is not new. It dates back to the work on nuclear magnetic resonance by, there is a pioneering work by Hahn, I think it's 1950, in which he essentially, this is a spin echo technique. And so he uses essentially he wants to have to increase the resolution in nuclear magnetic resonance and to suppress the inhomogeneity due to, for example, to magnetic fields that you cannot control. And okay, this is in 1950, and this idea was generalized and generalized to suppress generic system environment interaction in the essentially Viola and Lloyd and Mill in so this is 1980. And then there is a PRL 99, it's a seminal paper. And of course, there is also the contribution by Zanardi in 99. This is a PLA. So essentially, they generalize in this technique to generic system environment interaction. So let me start from just introducing the idea, and let us just look at finite dimensional system. So let's start here. So The idea is the following. We have an Hilbert space, finite dimension. The dimension is finite. And you have a certain Hamiltonian here. In HS. Okay. And the idea, as I told you, is just to apply unitary pulses. So this is time axis, this is time 0. And at time 0, you apply a pulse, let's say gamma 1, gamma 0. And then you let the system evolve with its Hamiltonian. So the system evolves between time 0 and time 1 with, so this Hamiltonian generates unitary group, the evolution. So you let the system evolve, and then you apply again the pulse, a different one, in general, gamma 1. Let the system evolve, let's say for a time tau. You apply again the pulse, and so on. You repeat this procedure. Let's say you have n pulses. Here, gamma and -1, the evolution. For example, just think at a qubit, a spin. So d is equal to 2. And in such a case, the pulses are unitary, unitary pulses. And this can be, I don't know, X, Y, Z identity. Okay, sigma X, sigma Y, sigma Z identity. Now, of course, if the pulses are just identity, you are doing nothing on the system. This is the free evolution of the system. And now the idea is just, can we conceive a suitable sequence of pulses such that the system which wants to evolve with the free evolution, this is time and tau, does not evolve. So essentially you just suppress the evolution of the system. And in order to do that, I need to introduce the concept of the decoupling set. So what is a decoupling set? The decoupling set is a finite set of unitaries. Right? Okay, so it's a finite subset of unitaries. And this will be essentially my possible controls, my possible pulses. Okay. For example, in the previous example, a decoupling set would be X, Y, Z identity.
Like the case of the quantum Zeno, right?
I will come to that. Yes, the difference is that here we have unitary pulses. I will comment later about quantum Zeno. In such a case, we will have projections of it. Yeah. Okay, so a decoupling set is a subset, a finite subset of unitary operators, such that the following property holds. Such that we have that if we average essentially over the decoupling set, so this is just the number of elements. So if we take the average, the X VDAG, this average is proportional to the identity. Okay, so this is just the identity operator times a proportionally big constant. Okay, so and this should be true for every X, every operator X in each case. Okay. So this is the requirement. The constant is not free. the constant is very easy to find. Essentially, if you take the trace of the first, the left-hand side, this should be equal to the trace of the right-hand side. Now, the trace of the left-hand side, this is just the trace of x. Okay. The trace of the right-hand side is d, if d is the dimension of HS. So here the constant is just trace of x divided by d, where d is the dimension of the space.
You choose the V set to be the while Heisenberg operators.
Yes.
The way, right? So is that the
Yes, yes, that's a possibility. No, it's not unique. There are many choices. In general, it doesn't need to be a group. It's just okay. The characterization of this set, I don't know, to tell the truth, but you can think at several.
Finding those is exactly equivalent to characterizing teleportation schemes or dense codings.
It's a one design.
It's the one say it's related to one design. Exactly, it's one design. Okay, so so this is what you require on the decoupling set. Now, in order to implement my procedure, my previous procedure, I have to understand how, what is the protocol. I have to decide which pulses to use. These pulses, of course, will be elements of the decoupling set. So I will introduce the concept of a decoupling cycle. Cycle of length. Okay.
What is the justification for having this condition?
Sorry?
What is the justification for having this condition?
I require this condition.
Yeah, why?
Why? Okay, because I want essentially to project. This is in fact a projection of any element of the algebra on the abelian, on the commutant. Essentially, let me say this is take x. Okay, it's a projection from B of H to the commutant, which in this case, of course, is just. And essentially, I want to average out any, I don't know the Hamiltonian. So I want to average out the Hamiltonian in such a way that the evolution is trivial, is essentially a phase. So the system does not evolve.
I wanted to, this is intrinsically finite dimensional, or one can push?
No.
This will be trace class. So you act on states, or because then you don't have maximally mixed state.
Yeah.
So you would act
So you're worrying about this thing, no?
Yeah.
Okay. This is finite dimensional, and I will talk later about how we can extend. Yeah.
But maybe that answer your question. So
Yeah.
can I say something?
Yeah. Sure.
No. So if D is infinite dimensional, you will not be able to find a finite set of V's,
Okay.
and then the sum would not even be well defined.
Mm.
So this capital V needs to be a finite set, and therefore D needs to be finite. Sorry, Paolo.
Oh, thank you. So, what is a decoupling cycle of length L? This is essentially a finite sequence, V1, V2, Vn, such that each element of the sequence, such that this sequence hits. So the elements are elements of the decoupling cycle. And in the sequence hits each element an equal number of times. Okay, so that means that essentially each element equal number. Okay, so that means that the length of the decoupling cycle should be a multiple. Okay. So that means that potentially n is a multiple. The simplest situation in which you get that n is equal to v, but in general you can. Okay, this is just the simplest idea. Of course, also this can be generalized. For example, instead of having a deterministic decoupling cycle, you can think at it in a probabilistic way. So you can just randomly draw your pulses, but with a uniform distribution. This is essentially the idea. And now, why I require this? Because it's immediate to see that if I take a decoupling cycle and I just average and just average an operator over a decoupling cycle, this is nothing but the average on the group. Okay, so this is nothing but the average. Sorry, on the group, on the decoupling set. Okay. Okay. And now essentially we are done, because given a decoupling cycle, we can decide our protocol. So we apply our pulses, gamma 0, gamma 1, gamma 2, in the following way. So the first pulse, gamma 0, will be, oh, I have to write from right to left. The first pulse is, let me check the convention. Okay, V1. This V1 double. This should be gamma 0. Then I have free evolution. Tau H. The second pulse, gamma 1, should be V1, V2 double. So this is gamma 0. This is gamma 1. And then free evolution. And you understand how you get V2, V3, dagger, and so on. And the last one is just V n dagger e to the minus I tau h v. Okay.
You have any assumption on the length tau that you do?
For the moment, tau is just a fixed length. Okay. So this is the choice of my protocol. So I take essentially gamma k is just vk plus 1 dag vk. So given a decoupling cycle, this is just a set of pulses that I use. And now you immediately see that I did this because, okay, let me call this U cycle. And this, the duration of U cycle is n tau, the total duration. Now you immediately see that these Vk are acting on the evolution with a joint action. So essentially, we can just exponentiate, we can move the joint action from the unitary to the Hamiltonian. Okay, so this is exactly equal to tau En H V n dagger e to the minus I tau V1 H V1 dagger. Okay. Essentially, this is nothing but e to the minus I tau Hn minus 1 H1, where, okay, hk is just say a rotation of h. This is what we get. And okay, just let me introduce just a shorthand notation for this. Otherwise,
Is this with a first order approximation or is this exact?
this is exact. You see, I'm just taking the unitary rotation transformation of this exponential. Okay. And this is also true for infinite dimensions.
The power series that is pulled inside.
In finite dimension, you just think of the power series. In infinite dimension, just use the spectral theorem. Okay. So no approximation up to now. This is exact. So let me introduce this notation. It is a product that is an ordered product. So like this, there is order from right to left. And K goes from 1 to capital N, and I get e to the minus I tau hk. Okay. Now you see that this is in a sense, is a different way, a different picture that you have. Here we have free evolution, and it's the same free evolution, interspersed by unitary kicks. But you can look at this as in the following way. You have for time tau, or a period time, or a period tau, you get that the system evolves with the Hamiltonian H1. Then for this period, for a period from tau, from 2 tau, it evolves with a different Hamiltonian, H2. And then you get a different Hamiltonian, H3, and so on. Okay. So essentially, you can trade this picture with this one. And this picture is essentially it's related to a generic situation, the situation you consider in quantum control when you have that the controls are piecewise constant. Okay. And more generally, this is related to product formula, Trotter product formula. So here you get a Trotter product formula, and I would like, I don't like this evolution. I would like to have something, this is my desideratum, I want this to be a phase. And the phase would be exactly the trace of the Hamiltonian. Okay, so let me call this phase H bar. So H bar would be this average. Okay. And now, since this average is equal to the average over the decoupling set, this is nothing but the trace of the Hamiltonian. Okay. So this is what I would like to achieve. Now, of course, if I know the Hamiltonian, maybe I can just construct the decoupling cycle in such a way that I get that equality. But remember, the rule of the game is that I don't know the Hamiltonian. Okay? I want to achieve this, whatever the Hamiltonian is. And in order to do that, the idea is just to use an idea from Trotter product formula. And this is related to your question. So now The idea is just to let tau to 0. Essentially, the frequency of the pulses should be higher and higher, so that the period should go to 0. Okay, so I want to look at the situation when tau is small.
I have one question, because implicitly in the way you've introduced the sequence is the fact that the pulses you are considering an impulsive limit, right?
Yes.
So the duration of the pulse is much smaller than tau.
Exactly.
But now you're going to make tau tending to 0.
Okay, so you're talking about the physical meaning of this. I'm just saying the following. The duration of the pulse, let me say tau d. This is, of course, much smaller than tau, which should be much smaller than the characteristic time of the meltdown.
Okay, but you are arguing that even with this condition having to hold, is it still legitimate now for you to take the tau tending to 0?
Yeah, essentially, okay, you can think like this. Just tau d, for example, is order tau squared. Okay, so, for example, suppose you take constant tau squared. But physically, this is exactly, so thank you for the comment. This is exactly what I have in mind. In fact, I will relax this point later. You don't need to have these strictly scales of time. In fact, one can do in a continuous way. Essentially, which is, okay, it depends on the physical situation you want to describe, but the pulses can be of the same order, the length of the pulses of tau. In such a case, on the other hand, we need additional condition. This is not enough. You need a decoupling cycle plus some additional condition. Essentially, you need what is called an Euler cycle. But if I have time, I will talk about it.
But that tau d is not part of the model, right? It's not seen mathematically. You don't see it anywhere, right?
Tau is here.
Tau d.
The length of
Tau d, no, tau d, in the mathematical model, tau d is 0. Yeah, exactly.
So going back to my question about whether the formula was exact, if you have a little bit of space in between your periods of H, and you can put the pulse in there, then it's exact. But if you don't, you need an approximation in small tau d, right?
Yeah.
So can I add something?
Yeah.
So what you implicitly assume is that you make the pulse so strong that you can neglect. So if you start from a kind of continuous picture where you have Hamiltonian with system bath interaction and you have control fields, in this picture you assume that you make the pulse so strong that on that time scale you can neglect the evolution of the system bath interaction. However, and I think you come to that, you don't need to assume that. You can formulate that exactly without making that assumption in a time continuous framework. This is typically called bang-bang, it's a delta functions roughly.
Exactly. Call impulsive limit.
Exactly.
Impulsive limit.
And in MR, for example, that is a very well valid, right? But if you go to other systems, that assumption is actually questionable. But the important point is the assumption is not needed. You can formulate that everything with continuous pulses of high frequency, they average then out basically the system environment.
The assumption is related to how much energy you are able to put in the pulses. The pulses is your control. So if you are able, the experimentalist is able to put as much as energy as want, of course, this is a good description. On the other hand, it might be, or it could be convenient to have a pulses with a controlled energy, but which just lasts for a long time. And in such a case, the description is different. Yeah. Okay. So I got this. So I want to look at this when tau goes to 0, And in fact, the idea is that, of course, you see when tau goes to 0, is also n tau goes to 0. The idea is just to repeat n times, repeat several times this decoupling cycle, okay, such that the total time is just fixed. By the way, let me look at what happened here. So this is what you expect, and this is very easy to prove. We are in a finite dimensional setting, so essentially, let me just, you get this product. This is just, so I'm talking about a Trotter product formula here. It's completely, and each of these, when tau is small, is just identity, is close to the identity. Okay, so this is just product of 1 minus I tau hk, and then you get plus order tau squared. So you get this, and okay, so, and now you just do the products. And so you get something which is 1 minus I, you get tau times the identity, so you get the sum A between 1 and then hk, and then you get second order terms, which I'm neglecting. So the tau squared. Okay, in fact, this is, if we want to be precise, this is n squared tau squared. Okay, but n is fixed, capital N, tau is going to 0. And so you see immediately that this is equal to exponential minus I tau n h bar. H bar, I recall you, is just the average. Okay, h bar, let me call it, write it here. It's just 1 over n, the sum of h plus order n squared. Okay.
So you don't want n tau converging to a fixed time. You don't.
No, n is fixed. N is a fixed multiple of A. For example, n is just the dimension of A. It's fixed. This is just the number of pulses in a cycle, just the length of my decoupling cycle. Okay. So I get this, and this is okay. This is exactly what I to have. But now this is not the game. The game is just to repeat the cycle times, because you see here I'm just looking at a very short time evolution of my system. This is exponential, but tau n is very small. I want to look what happens at my system in a finite time. Okay. So essentially, what I'm interested in is the following. It's just U cycle. This is U cycle for a times n tau. And this approximation is true when tau is small, is going to 0. So I want to look at this U cycle for a time t over n to the power n. So I'm repeating my cycle n times, and the total duration of the cycle is t over n. It's okay. Is it clear? So, and I will eventually look at the limit n to infinity. Okay. So the duration of the cycle is smaller and smaller And you have a larger and larger number of cycles of repetition. Okay, now, now what one can prove, and this is just Trotter product formula, is just a limit of this when n goes to infinity, is essentially this one. So it's just okay, you can prove it from there, let's say. So okay, let me write this. This is just e to the minus I. Now tau is, you see, now tau is t over n capital N. Okay. So this is t over n capital N h bar plus order n squared t squared over, so I have t squared over n squared. Okay, this is equality to the power n. And so you immediately see, and this goes to t. Wrong.
You missed capital N.
N drops out.
Component.
Ah, because yeah. So okay, there is an N there. Thank you. T h bar, which is a phase, as I told you. So this is nothing but e to the minus I t, the trace h over t, and that's it, times the identity. Of course, this is, you see, essentially, this is the limit. One can have, one is interesting in application. It's the rate of convergence of this limit. I mean, this is exactly related to what we were saying before. The limit n to infinity, what is the physical meaning of the limit n to infinity? I should say to my colleague, you have to repeat the cycle 100 times. That's enough, or 10 times. This is infinite. So I have to look at what is the error. Essentially, the rate of convergence from this quantity to that. And okay, I will use my favorite technology in order to compute this rate of convergence. And this is yeah, this is okay, this is related to a bound, a generic bound. Let me call it bound of the ring. And this is just a paper by Daniel. And, the alphabetical order, I don't remember. Here, okay, we should do me, and then Gramegna. Yeah. This is quantum 2022. 2022. Yeah. And this is a universal bound. In fact, it's very nice. I like it a lot. But so you have two unitary evolution, just I mean, two unitary propagators just generated by time-dependent Hamiltonians, so you don't need. And you want to give a bound to the difference between to the divergence between the two evolution. So essentially, here I get U1, here I get U2. And I want to give a bound to this divergence. Okay, at time t. And the proof is very simple, is astonishingly simple, but the bound is very useful in many situations, for example, in trotter. And so you can bound this. Of course, we know you can bound this. The most trivial bound is just bound this by the difference of the Hamiltonian. So the most trivial one would be just bound this by this quantity, H1s minus H1. Okay. This is essentially perturbation theory. It's very easy. But it doesn't work in this case, essentially, because what is important here is just the cancellations. So I need phases. I mean, it's not enough to take the norm. So essentially, the one bound I was talking about is the following. You can bound this by S21 of t plus the integral between 0 and t d x, and then I get S21 of x H1 of x plus H2. Where S21 of t, this is just the integral of the difference of the integral. Is an action, okay? It's an action. Action. And now you see, even if okay, this is much useful. I mean, or the fact that here you're taking into account an averaging effect. Okay. What I mean is that the contribution of this difference over a certain period of time can compensate the contribution over a different period of time. At this level, this is impossible because this is positive. But here you can have compensation. So it can happen that this, and this is exactly the case, for example, for trotter. Then this quantity is of order 1. This quantity is of order 1. However, this quantity due to compensation is of order 1 over n. In fact, this is the usual idea. You can have an integrand function which is order 1 but is fast oscillating. When you integrate it, the integral is of order 1 over n. This is exactly that idea. So essentially, this is the one bound, the bound of the ring. And now it's very easy to see that what's happening in our situation. In our situation, we have is a trotter product formula with different Hamiltonian. So essentially, the evolution here is just an evolution which is generated by a time-dependent Hamiltonian, piecewise constant. Is exactly this picture, no? H1, H2, H3, and so on. The second evolution, on the other hand, is just a unitary group. Okay, so this is just e to the minus I t h bar. And this is nothing but the product. Okay, what I write here. Okay, so here you get e to the minus I t, I don't know. It's a product. Okay, it's exactly that picture with many cycles repeated. Okay, and now you just input this here, and you immediately see now what is the norm of hk, of h1 of t. H1 of t is just, depending on time, is just a certain vk H decay dagger. So this is equal to, this is equal to H. No, because this is equal to VK H VK dagger for a certain K, it depends on time. Okay. For example, I don't know if I'm looking here, is the norm of H3, which is equal to the norm of H. So this is H. This is H. So essentially, this is 2 times the norm of H. Okay. And this goes out the integral. So at the very end, I have, let us look at the action. The action on the other hand, here I get a constant Hamiltonian. Let me write it here. The action. The action is just the integral between 0 and t in the S. And here I get H2 of S minus H bar. Okay. H2 of S is something which is H1, then it is H2, H3, and so on, depending on the period. So essentially, this is, you immediately see that it is just the average. Okay. So this is nothing but the average. The sum over K of HK times T over NM.
Yeah, this is not H2, that H2, but it's just the second one you're comparing with.
Yeah, this is H2 of S, sorry for the notation, the second one. Okay, minus T times H1. Essentially, it is not difficult to see that this quantity is of order T over N. But it depends also on the norm of H. Okay. I mean, for very particular times, if the time are exactly the time of a cycle, the end of a cycle, this is exactly equal to 0. At the intermediate time, you need some Hamiltonian in the sum here in order to complete the cycle. And this is essentially the order 1 over n you have. The norm of H is exactly the norm of this. Is it okay? So essentially you see that the action is of order 1 over n. And if you put the things together, we have that you cycle T over n to the power n minus the average revolution. This is less or equal than the norm of the action, which is, okay, I can tell you exactly. It's essentially 2T over NH. Times, again, the norm of the action, plus 2H. So it's 1 plus 2H. These are constant. The norm of the action is exactly that 1. And this is T times the sum of this. Okay. So essentially, okay, maybe I'm boring you. Okay, this is just the result. So, I mean, you can, the message is that, of course, in the finite dimensional case, you can have explicit bounds, and the important message is that the error convergence, the rate of convergence of the error is of order 1/n. Okay, so the convergence is of order 1/n. It is the finite dimensional case. Okay, this is the important message. And now we go to something maybe more interesting, which is the case of my initial purpose was to suppress the interaction between system and environment. But up to now, I just consider the system itself. So the situation I want to control, the situation which I have system plus environment. So my Hilbert space is just Hilbert space of the system, which I still consider a finite dimensional system, times the Hilbert space of the environment.
In this, now, any choice of unitaries would have done, right? The
Sorry?
final theorem does not depend upon which unitaries you chose or
It's completely
order, it doesn't matter at all.
exact. This theorem, you don't need to have a decoupling cycle, whatever it is. Okay. You just if the unitary is if this is a decoupling cycle, this is just proportional to the identity. Otherwise, it's just the average. Okay. So the situation is the following. And so, as I told you, you can act on the system only. Essentially, okay, this is quite easy. I just promote my decoupling cycle, which is acting on the system, to a unitary on the larger system. So essentially, the evolution will be the following. So I have an Hamiltonian on the total system, Hamiltonian H on the social system, possibly unbounded because the environment could be unbounded. And the decoupling side, I have to do the following procedure. E over n to the power n. I want to look at it. And this is nothing but the product k between 1 and n. Now I get that the decoupling cycle Vk is acting on the first factor on the system. And I get e to the minus I t, t n capital N h b k DAG identity. And this is exactly what this is, sorry, for a cycle. And I want to repeat. You want to look at this. Again, as I told you before, this adjoint action can be moved on the exponent, no problem. Okay, essentially, you're just unitarily rotating the domain of your Hamiltonian. Everything works perfectly. And so I get hk to the power n. Now the question is, does this limit exist? And if it exists, what is the limit? And more difficult question, what is the convergence rate to the limit? And as we know, in the case of unbounded operator, of course, all this stuff, you see, from the very beginning, using the fact that the operator is bounded. So, and I take everything in the non-convergent sense. Of course, the group itself is not normal continuous. Okay, so you immediately expect that, of course, the first reasonable topology that you have to look at is just the strong topology, strong operator topology. So essentially, I'm interested in this limit. For example, I prepare, this is the usual setting, now I prepare the system, okay, whatever. I want to look at this limit over a given state psi of system environment. Okay. And so I'm interested essentially in the strong topology of this. So the strong limit n to infinity of u psi e over n to the power n. Okay, I'm interested in it. And so you immediately see that if the limit exists, suppose the limit exists. If the limit exists, the convergence depends on the state. Okay. So there are states which are well behaved, and so they give you a good convergence rate, which is essentially 1 over n. There are states which are much okay. I think Alexander is going to talk about this. So it's let me say just something very general, because I don't want to spoil his talk. It's reasonable, physically reasonable, that the limit should depend on state. Because, okay, it's okay. This, for example, you can take a state which is a factorized state. So you are choosing the state of the environment, for example, a thermal state. And if you have strong convergence, given the state of the environment, you have essentially uniform control on the system. Okay? So given the state of the environment, essentially everything is similar to what I did for a finite or a bounded Hamiltonian. Okay. But in general, let me say this limit might not exist. And this is the usual, is essentially related to the difficulties you encounter in product formulas. Okay. So in such a case, we will say that the dynamical decoupling works. We will say that dynamical decoupling works if the following things happens: if the limit exists, and the limit is exactly what you would get in the finite dimensional case. I mean, it's a factorized evolution. It's an evolution of the form identity on the systems times evolution of the bat. Sorry. Where B is a self-adjoint operator. The bat. In other words, I'm saying, it's another way to write this, that I get something like this. Okay. And let's say, so I repeat, dynamical decoupling works if the strong limit of this exists, and is exactly what I want. You see, maybe I should comment on this. In this product space, the trace is replaced by the partial trace on the subsystem. Okay, so if you take the partial trace on the subsystem, if everything works, of course you get something. In general, you get a non-trivial evolution of the environment. But the environment evolves, but we don't care about that. Because you see, the interaction between system and environment was suppressed, is no longer there. The system does not evolve. Okay? Okay. Now, the problem of the existence of this limit is not easy. As I told you, this is related to Trotter product formula. And of course, I can state a general theorem, which is related to Trotter product formula. This is something Arendt's this is Journal Mathematical Physics 18. But it is essentially an observation. And the observation is that you can just state sufficient condition for the existence of that limit. And it's not difficult to see that under this sufficient condition, the limit is exactly this one. It's factorized. And the sufficient condition is just the sufficient condition of Trotter product formula. Essentially, you require, let me say that, what's written there? It's not written. You require that the sum of the identity H, the identity that this quantity is essentially self-adjoint. Okay, essentially this is the sum of H1, H2, Hn. This should be essentially self-adjoint on the intersection domain, on the common domain. On the intersection domain is just a rotation, so V1 over D of H. Okay, the intersection. Essentially, I'm saying that the operators, the rotated operators, okay, say this, are compatible in the sense sufficiently compatible, such that the intersection of the domain is a domain of essentially self-adjointness. And so the limit would be essentially the closure of this. This is a trivial generalization of Trotter for n terms instead of 2. Okay. 10 minutes.
Sorry,
Yes.
but I think I don't understand the comment you made on the dependence on really the initial state.
On state.
That's because,
Which comment?
well, to me, it really looks like the existence of the limit and the, well, good convergence does depend on the structural form of the system environment coupling.
Exactly. This depends on the state. No, it's okay. If you take a state of the environment with a certain temperature or with a different temperature, this changes.
But the statement was just, I think, if the convergence rate is independent of the state, you have actually non-convergence.
Yeah.
And that is a much too strong thing that you couldn't possibly expect that in.
It doesn't work already at this level. So suppose you have just identity pulses. This is not non-convergent if H is unbounded. If and only if H is unbounded.
In this scenario, it still exists for all states, but the rate depends.
Okay.
Has to depend on the state.
The rate depends on state.
So it's
And
actually combined, right?
Exactly,
So
it's
you have
combined.
conditions that depend really on the form of the coupling, if you want, and then subsequently this also
On the state of the environment.
right. Yeah, okay, fine.
In some sense, that's also consistent with the picture of the spectral density, where you have
Exactly, that's what's
the
precisely
structure
what
of
I
the
was
bath
thinking,
coupling
yeah.
acting on the state of particular
Absolutely.
bath
Okay.
states. Yeah.
Okay. So 7 minutes. Okay, what can we say about this situation? Okay, Alexander will say something about it. I just want to say something about maybe a comment about time scales. So physically, which is very related to your question. So if we look at the evolution of the system, can we infer from the evolution of the system what is the correct time scale? And so essentially, the idea is the following. This is mutuated from the idea of quantum Zeno effect, quantum Zeno dynamics. So suppose I replace my unitary pulses by projection. So I replace my gamma k by a projection operator. So in such a case, the product formula will become U cycle of n tau will become P e to the minus I tau H P n times. Okay. And so in general, what I get is that if I repeat this n times, I will get something like this. I'm just replacing formally my unitary kicks by projection. Okay, this projection can be interpreted, for example, as projective measurement, Neumann. And so you're just measure the system, let it evolve, measure, let it evolve, measure, and so on. Okay. Now, if H is bounded, it's very easy to see that this is just HP. Okay. In particular, if you project on a rank 1 projection, something like this, you get that this quantity is very easy because you get that P e to the minus I. Okay, let me write. Let's suppose that n equal 1.
But are you replacing all the pulses with the same projection?
With the same projection. Sorry. All the pulses with the same projection. Of course, we can play a lot, we can move projections, but okay, I just want. So in such a case, you get, this is very easy, this is nothing but the projection, and then you get a survival amplitude. You get psi e to the minus I th psi. Okay. Let me call this A of t. And now it's very easy to see that.
Small n missing.
Sorry?
Small n missing.
Yeah, you're right. Running out of time. Okay. So I have to look at the limit of A t over n to the power n. And now, if psi is in the domain of the Hamiltonian, I can just, it's very easy to see that the A of t goes like 1 minus I, the expectation value, H over psi, t minus 1/2, and I get H psi squared t squared. Okay, plus small order. This is for t that goes to 0. Now, essentially, if I look at the survival probability, which is the modulus square of this is quadratic. Okay, so if the state belongs to the domain of the Hamiltonian, this is quadratic. For small time. Okay. Essentially, the picture is the following. This is the survival probability with no measurement. It's quadratic for small time. It's quadratic. Now, suppose you measure with a certain tau. Here, you get a projection. You get a projection, you are projecting the state back. So the survival probability will be like this. So this is with one measurement. Now, suppose you repeat this, be like this, and so on. So you see, this is the free probability, the probability without measurement, and this is the probability with measurement, with the period tau. Now, suppose I measure with period which is half of this. I will get something like this. I'm not good at drawing the point. I think you can imagine what is happening. So you see that this is the free evolution. This is the evolution with a certain period of x. This is the evolution with another period, with a shorter period, and so on. So it's very easy to see that due to this quadratic behavior at short time, the limit of this goes just to the projection times the phase. Okay, so it seems that this initial quadratic behavior is essential. Okay. Let me just comment on this. If psi is not in the domain of the Hamiltonian, you can have a linear behavior, for example. In fact, there is a theorem, it's quite simple. It's from Exner, I think. Exner, 2005. Physics letters, I think. So essentially, if you look at the spectral representation of H, you get that if psi is in the domain of H alpha over 2, then the probability goes like 1 minus order e to the power alpha. Okay. So if psi is in the domain of the Hamiltonian alpha equal 2, you get quadratic behavior. If it is in the domain of H1 alpha, you can have exponential behavior, 1 minus 10. And now the point is that if this curve is exponential, is linear, no matter what we do with measurement, we will obtain the same curve. Okay. So you see that
Can you please repeat that sentence?
if the curve is exponential, if the probability E of t goes like 1 minus gamma t for short time, you get that if you take pt to the n to the power n, you will get e to the minus gamma t. So you cannot affect the evolution by pulses. Doesn't matter how frequent they are. Okay, so again, this is an instance of the fact that it depends on the state you're acting in. Okay, and I would have a lot to say, but I think I can. Okay, let me just one last comments, because this maybe could be useful for Christian. And the idea, look here at this. If psi is in the domain with alpha less than 1, you get a behavior which is sublimate. Okay. This is the linear behavior. You have something like this, for example, square roots. In such a case, if you frequently measure the system, you will get that you accelerate the decay. You have even the opposite effect that you expect. So, and this is called inverse Zinn effect, anti-Zinn effect. It depends on the.
Thank you for saying that. But what I actually just need is the convergence results. It has, when I say speeding up quantum dynamics, it has nothing to do with that.
Okay. Okay.
But I appreciate what you have established already.
Okay, we'll stop here. Thank you very much.